we can adjust the reactivity and adjust how it sets and breaks by using different formulations. So let's talk a little bit about what is an emulsion. Basically, an emulsion is a mixture of two different liquids that are not miscible in each other. So they're not soluble in each other. So like oil and water. So an emulsion is a dispersion of one liquid in another one. It's different than a solution. Some emulsions that we commonly have around the house are milk, which is a dispersion of milk, fat, and protein in water. Lotions and creams. Paint is a good example of an emulsion that we use at home, and also butter. There are different types of emulsion. So if you look at the pictures on the right-hand side, the top one is an oil and water emulsion. So we have droplets of oil dispersed in water as a continuous phase. An asphalt emulsion is an example of this. The next one is water and oil. So that would be like butter. So fat is the continuous phase with little droplets of water dispersed in it. We can also have multiple emulsions. So the bottom picture shows oil and water in oil. So you can see little bitty droplets of water inside of the oil droplets. If we look at the picture of the asphalt emulsion, you can see that, when we look at an asphalt emulsion, right, it's brown, it's opaque, you can't see any of the droplets. The droplets are really small. In this picture, the scale is like 100 microns across the whole picture. A micron is 1,000th of a meter. So a typical asphalt emulsion droplet is going to be between 1 and 20 microns in diameter. So they're pretty small. For reference, your hair is about 70 to 100 microns in diameter. So we can see there's a distribution of different droplet sizes, and in some cases there are droplets within droplets in an asphalt emulsion, so a multiple emulsion. The components of emulsion, well, the main components are asphalt binder, water, and then chemicals. So the chemicals are really a small percentage of the asphalt emulsion, but they're a really important part. They give stability to the emulsion, and they also give it the reactivity characteristics that we want to have in our emulsion. There are other components such as solvents and polymers that we add to modify the properties of the emulsion. So just a little bit more about these raw materials that we use for emulsion manufacturing. The asphalt binder generally is similar to the materials we use in hot mix paving. We grade the asphalt binder into grades by performance grading, like PG64-22, or pen grades, like penetration. These are basically ways of measuring the viscosity of the asphalt. And the choice of the asphalt binder, the grade, depends on the application that you're going to use the emulsion for. Water. So the water is generally potable water, so clean water without a lot of suspended solids or minerals. We don't want to have solids or minerals in there because those are places where the asphalt droplets can stick to and start to sieve up and destabilize our emulsion. Some emulsions, particularly anionic, may require that hard water is softened in order to make stable emulsions. Polymer can be added in the emulsion either as like latex, SBR latex, which is a dispersion of latex and water, or also in forms like SBS, which can be dispersed in the asphalt binder itself. The polymer adds elastic properties that help improve the performance of your final product. Solvent may be used because these could be hydrocarbon solvents like mineral spirits or fuel oil or some biosolvents. Now, these can be added to emulsions for different reasons. Some of them are to give workability to the mixtures with aggregates, or to give better coating of the aggregates or the fines on the aggregates, and also to soften the final residue of the asphalt binder after everything is set. The emulsifier. So this is a really key component. This is the chemical that's in your soap solution, which is used to stabilize the emulsion. It also allows you to design and formulate the type of emulsion that you want to get the right performance that you want. These types of chemicals, these emulsifiers, are also known as surfactants, and they're typically derived from like natural fats and oils like beef fat or like tall oil, which comes from pine trees. Thickeners can be added to the water phase of your emulsion, water-soluble polymers. These help to improve the storage stability of the emulsion to prevent any settlement of the droplets and also to increase the viscosity of that water phase. Salts are another component that can be added to the emulsion. These are typically sodium chloride or calcium chloride, and their main function, well, one of the main functions that they have is to stabilize viscosity changes in the emulsion. For example, in CRS emulsions used for chip seal, these are high viscosity emulsions, and if there's any salt left over in the asphalt binding from the asphalt binder from the refining process, this tends to build viscosity in the emulsion. So if you add salt to the soak phase, this helps to balance things out and keep your viscosity more stable, a little bit lower, but more stable over time. Anti-strips are chemicals that are used to help the asphalt binder stick better to the aggregates. Sometimes these have to be used, and they could be either added to your asphalt binder, post-added to your emulsion, or added in the soap solution, depending on the type of emulsion and the type of product. So emulsifiers are really important because without them, the asphalt and the water will quickly separate, so you won't have a stable emulsion. So you can think about it as with a salad dressing. So if you have, salad dressing has oil and like a water vinegar phase. So if you shake it up, the oil is dispersed in that water phase. But as soon as you stop shaking, it starts to separate. So you'll have two phases again, so the water and the oil, if you don't have an emulsifier like egg yolk or something in the salad dressing. It's the same concept with asphalt emulsion. You add energy when you put the asphalt in the soap solution through the Colloid Mill. But if you don't have a stabilizer, an emulsifier, or if you don't have enough emulsifier or the right one, you will have phase separation and you won't have a stable emulsion. So let's think about how the emulsifier actually works to stabilize the emulsion. We'll talk a little bit more in detail later, but just think about, this is a simple concept. It's all about the charge. So what the emulsifier does is it puts a charge on the surface of the asphalt droplets within the emulsion. And for a cationic emulsion, it puts a positive charge on the surface of the droplets. So these like charges repel each other, kind of like a magnet. So if you have two magnets that you try to put the two north poles together, you can actually feel them repel each other. So it's the same type of thing. These opposite charges, these like charges are repelling each other, and they keep the droplets from sticking together.
Keep it in.
For anionic emulsions, it's the opposite charge. So we have a negative charge on the surface of the droplet. And that's what keeps the droplets apart. So where does the charge come from? It actually comes from the emulsifier. So when we take we look at this slide, we kind of have a simplified structure of an emulsifier molecule that has like the big blue dot with the tail on it. So on the top diagram, that's a cationic emulsifier. In the head group, there tends to be a nitrogen atom, which is able to accept a positive charge, also called, you might hear people say, a protonate. So when you mix the cationic emulsifier with water and acid, when you're making your cationic soap solution, that's the acid activates that emulsifier by putting that charge on the head group, by protonating that head group, putting that positive charge on there. For an anionic emulsion, it's the opposite charge. So an anionic emulsifier would have a molecule like oxygen in the head group, which will accept a negative charge. So when you make your soap solution, you add your water, your anionic emulsifier, and your alkali like sodium hydroxide, and this is what's activating that emulsifier and putting that negative charge on the head group. Some emulsifiers do not need acid or alkali. They have a permanent charge. And then just to be complete, I also wanted to mention that there are some emulsifiers that don't have a charge at all. So they're called non-ionics. And that's this big one on the bottom with the this big head group, and the way that they stabilize the emulsion is they have this big, giant, floppy head group on them, so they make a physical barrier around the droplet that prevents the droplets from agglomerating together. So it's that emulsifier structure that allows it to, put its head group on the surface of the droplet and its tail in the asphalt. And it's because of that structure, the head group is polar, it's hydrophilic, water-loving, and the tail group is oily, so it's fat-loving. So when you have a mixture of oil and water, that surfactant or that emulsifier is going to go to that surface, that interface between the oil and the water, and orient itself like that. So it's that structure and the chemistry that actually allows the emulsifier to be in the right place in order to get onto the surface of the asphalt droplet when you manufacture the emulsion in the colloid mill. So that's a little bit about the chemistry. So now I'll turn it over to Joe to talk more about the emulsion manufacture.
All right, thanks, Christine. So this portion of the presentation is going to talk about the manufacturing. I am going to ask everyone to please mute your phones or your computers. We're getting some feedback here. So anyway, as you can see here, we have a colloid mill. It's open, so you can see the rotor and the stator. The rotor is the piece of the tooling that actually spins. That's connected to a bearing module, typically or directly mounted to a motor. The portion of the mill that's kind of laying or that's parallel to the ground that's open, that's the stator, and you'll get a better picture of that later on. But all of the shear takes place in this mill, and when I mean by shear, I mean by hydraulic shear. When we think about shear, we think about like scissors, where we're cutting paper, or we're shearing hair to get our hair cut. Well, there are what we call teeth, and hopefully you can see from this picture that we have rings of teeth. Well, these teeth actually are the mechanism that shears the asphalt into small droplets, but it's hydraulic shear. So the asphalt is being stretched and pulled and kind of torn apart into really tiny particles, like Christine said. We're looking for particles around 5 microns in diameter. Well, 1,000 microns is 1 millimeter, so they're really tiny particles. And all this really happens in a fraction of a second as we are injecting our asphalt in our soap, and our solvent, and our latex, or whatever we're using to make our emulsion. This happens very, very quickly. And the one thing to keep in mind is that I get asked a lot, well, what's the difference between a emulsion mill and a polymer mill? A polymer mill being that you take styrene, butadiene, styrene, co-block polymer, and you shear it into asphalt. And really, it's the tooling. Being the rotor and the stator. Again, what you're seeing here is a picture of the rotor and stator, but this is for an emulsion mill. So the tooling is more of like a stainless steel, hardened stainless steel that can withstand acid from manufacturing cationic emulsions, whereas a mill that would be used to manufacture, say, SBS, modified asphalt, either for hot mix or for emulsification, that's more of a hardened steel that can withstand high temperatures, high shear, and just a lot of tearing. So in order for this to all happen, we need to have high pressure, we need to have heat, and obviously the most important part is the chemistry, because as Christine said, the chemistry really kind of dictates what you're making, whether it's a slow set or a rapid set, quick set, a cationic or an anionic. So if you look at this basic schematic of a batch plant, you'll see on the left is our asphalt tank. And typically we keep our asphalt between 250 and 300 Fahrenheit, and that depends on the type of binder that we use, whether it's modified with SBS or unmodified. We also have typically tanks for emulsifiers. That's tanks, whether it's cationic or anionic. We have acid or alkali tanks. We also have tanks for stabilizers as well. Now, if you notice on the bottom, we have a red solvent little injection line and a latex injection line. And the reason why I talk about those is because, as Christine mentioned earlier, solvent can be used in many different ways. It can be used to help with adhesion of the stone, especially if your stone's dirty on a chip seal. It can also be used to really soften the binder based on the specification that the manufacturer is trying to meet. Latex, which is it's a styrene butadiene rubber. This is also an emulsion. Basically, you have small polymer particles that are suspended in a soap solution, and this latex, can be used, in many different applications, whether it's chip seal, microsurfacing, some other applications, depending on whatever the manufacturer decides to make. But that can be injected or added into certain points within this batch plant, and I'll go into that later. So here you have a batch plant that is mounted on a skid. At the very center of the picture, you see this blue motor, and then to the left of that blue motor, you see this gray piece of equipment. That's the Colloid Mill. And this mill is directly mounted onto the motor. Now, some mills, as I showed before in a previous two slides, that's actually mounted to a bearing module, so you can kind of help control the RPMs a bit of the mill. But this is basically where all the shear happens. So, we have the two components that really meet at the center of the mill. They go right through the stator being stationary, and that's mounted on the back side of the Colloid Mill. And the rotor, which spins, that's directly connected either to a bearing module or to the motor itself, spinning, and then out comes the emulsion. So one of the, really I think the most important part of manufacturing emulsions, outside of knowing what asphalt you're going to use and kind of understanding, the properties of that asphalt is, well, how do I manufacture soap? And why is soap preparation so important? Now, depending on the emulsifier that you use, you could either make up a straight soap solution in your batch tank, or sometimes you could make what we call a soap concentrate. And sometimes it's nice to make up a soap concentrate because you can either store it for later and then dilute it as you need it to make up your soap solution for that batch, or there are some emulsifiers that require elevated temperatures in order to protonate or to make up a soap solution. So depending on what you manufacture and what chemistry you use, you may need to manufacture your soap differently. I'm going to get into this a bit later, but how important it is to understand temperatures. Temperatures play just a super critical role when we manufacture our emulsions. The reason being is because if we have a asphalt that is super high in viscosity, that means that we have to have that asphalt at an elevated temperature in order so it's pumpable. And once it's elevated in temperature, say like 300 plus degrees, even hotter, then when that soap solution meets at the mill head, we could produce an emulsion that's boiling, that's over 312 Fahrenheit. And anyone who's manufactured emulsions knows that that's kind of a bad day if you're making emulsion and it's boiling off the mill. So I'm going to get into the temperatures a bit more, and then how to kind of avoid boiling off the mill. So when you make up your soap, also depending on the emulsifier, you can either add your acid or your alkaline first or last. I think in most cases, how we kind of start making up our soap solution is we start with warm water. We add X amount of percent of our alkali or acid. Then we introduce the emulsifier, begin to react it, to protonate it, and then we kind of top off the tank with water, and then from there we can kind of pH up or down based on what we're trying to make. There are some emulsifiers that are completely soluble within water, and they don't need an adjustment. These are pretty nice emulsifiers to use because it kind of saves time. But again, not every emulsifier will meet your needs. So you kind of have to talk to your vendor to really kind of figure out, like, well, what works in this system and what's going to give me the best emulsion. One thing to keep in mind when I used to test soap solutions is that the soap really should be clear for the most part. It's always good to grab a sample of that soap, pH it, but then also take a look at it. It shouldn't be cloudy, generally speaking, and it's always good to kind of look at the soap solution, make sure you don't see any droplets of unsaponified or unprotonated emulsifier kind of floating around. Because with that, so if you have emulsifier that's not reacted, and you add, say your pH, say you're making a cationic, and you have kind of emulsifier floating around, and you've added your acid, that can kind of give you a false pH. So you think that, hey, I'm at a 2 pH, let's go and fire up the mill and run with it. But if you have soap or emulsifier that's unreacted, that's going to adversely affect your emulsion. So it's always good to take a sample of your soap solution, visually look at it, make sure you don't have any unsaponified or unprotonated emulsifier. We also can add additives to our soap. They could be latex or thickeners. And again, it kind of depends on the order of addition and what you're making and what emulsifiers you're using. So, if you need to add latex to your soap tank or thickeners, make sure you talk to your vendor, and they'll give you the proper order of addition. So here you see it's the soap tanks that are actually connected to the batch plant that I showed you earlier. These are, I think, 1,000-gallon, maybe a little bit more, soap tanks that are inside. One thing to keep in mind is when you look inside of the soap tank, you've got two aspects of the soap tank that I think are really critical. Aside from the tank being stainless steel, you have an agitator on top. One of the most, or I think probably the most important thing to have on a soap tank is good mixing. It'll just help out the reaction. It'll speed things up, and also at the bottom you see coils as well. So if you don't have, say, a water heater or a tank with warm water, having coils in a soap tank really is invaluable in my opinion, and can really help you speed up your manufacturing and give you better quality emulsion. And later on in my talk, I'm going to give you an example or a calculation to use in order to determine the proper temperatures based on kind of what you're trying to meet, like what your goal is. And here's just a picture of the finished soap. As you can see, there's suds on top. It is pretty common if you have an open tank to get on a ladder or a catwalk and take a hose and kind of spray off the suds, just kind of get lower or reduce the amount of suds, because one thing I've seen happen is as you begin to fill up the water, the suds can kind of roll over the side of the tank. So one thing you might want to do is take a hose and just kind of knock those suds down. I wanted to talk a little bit about how we manufacture emulsions with latex, and I think it's pretty unique how you can add latex to your emulsion. Really, I think you've got 3 different ways in order to add latex. And as Christine mentioned before, latex or a polymer is meant to give elasticity to your binder. It helps with stone retention. it kind of gives it that ductile force where it can be, stretched, without tearing, without breaking. And the most common way that I know is, adding latex to the soap solution prior to the mill. So if you see here in this schematic, the latex is being injected in between the soap tank and the tank for the emulsion. You can also post-add latex to emulsion. Just make sure that if you're making an anionic or cationic emulsion, that you're dealing with the same charged latex. But keep it in mind that when you post-add latex to an emulsion, you're typically, or generally speaking, you're going to lower the viscosity of your emulsion, and it's also quite difficult to have that latex completely dispersed. And also, you're going to have agitation in that tank. So, unless you absolutely have to, I don't really recommend adding latex, after you made your emulsion. But again, it kind of depends on what you're trying to do, what you're trying to make. Third, you can also add latex to your asphalt. The one thing I like about adding latex to your asphalt is that if you have issues with viscosity, adding latex to your asphalt, generally speaking, will add viscosity to your emulsion. But again, I think it's one of those things that you to trial in the lab first, maybe talk to your latex manufacturer to see if that's the right, way for you to go in order to produce. There's a question here I'm going to actually answer real quick. I guess the question went away. It says the heating of the soap tank. Okay, so time to heat up the soap tank, I guess it depends on the emulsifier that you use. Kind of going back, certain emulsifiers will take longer to protonate than others. So again, talk to your manufacturer. There are some factors that affect emulsion quality. We have asphalt and water flows, kind of like your process conditions. The one thing to keep in mind is that you never want to starve your mill. And what I mean by starving, if your mill is meant for, say, 20 tons per hour, you should really feed it around 20 tons per hour, because if you starve the mill will begin to cavitate, and you can kind of hear it pulse. And what's happening is that you have small little soap pockets inside of the mill head, kind of turning it into steam, so the back pressure is spiking, and what that'll do is it'll give you an uneven particle size distribution. So that's one thing to keep in mind. To make sure that your mill is being properly fed, and that you understand that that the asphalt and the water flows or soap flows really are consistent. So I don't really go into pumps too much, but one of I think the most consistent pumps that I've seen for like water and for latex or the progressive cavity pumps are like those the mono pumps. Fantastic pumps. They really will feed the mill consistently. They're easy to adjust. They're variable speed. Temperatures will also definitely affect emulsion quality. Again, if your soap is, say, too cold and your asphalt's too hot or too cold, that will really, or it can, negatively impact the quality of your emulsion, because even though the shearing happens, inside the mill, you really want to have the temperatures as close together as you possibly can. So, warm soap and a fairly cool asphalt, but asphalt that can be pumpable and the viscosity is such that it can still be sheared. But you're trying to find that right temperature. And then also, again, you don't want to have your asphalt so hot or your soap so hot that you are boiling off the mill. And the more asphalt that you put into your emulsion, you can expect the higher a temperature is off the mill of your emulsion, your exit temperature. So just keep that in mind. Like if you're making a tack coat and your residue is, say, 57 to 60, versus a high residue chip seal, your temperature coming off the mill is going to be quite different. Gap. The gap is what we call the mill gap, and that's the distance between the rotor and the stator. Typically, that is between like 1 to 3 millimeters, and I'll go into that more in detail, kind of the pros and cons of adjusting your gap. Back pressure. That's another aspect that can definitely affect the quality of your emulsion. You really want back pressure from the very beginning to the very end to be consistent. Speed of the mill, that's the rotation or the RPM of the rotor. I don't know too many production mills that you can change the speed of the rotor, but that can definitely affect the quality of your emulsion, and then also size of the mill. Sometimes you're feeding the mill not enough or too much, and again, trying to have that balance between hey, we need to produce this really quickly. We need a good production rate, but we don't want to push the mill too hard. But then again, we want to make sure that we feed the mill how it was designed. Also, emulsion handling, that can definitely affect your emulsion quality. I'm going to go into that a bit later. And then chemistry. Christy touched upon that quite a bit, but really kind of choosing the right chemistry for what you're trying to make, and just understanding how the soap is made, what to expect out of your chemistry. For example, there's a lot more chemistry, generally speaking, in a tack coat versus a chemistry in a CRS 2P. So they're going to act differently. They may handle differently. So I'm going to talk a little bit about your flow rates and residence time. And when we think about residence time, so as we're making our emulsion, that is the amount of time that the asphalt and the soap have in the mill in order to be sheared. Well, best practices says that there should be a back pressure valve, after the exit on the mill, so we can kind of control the back pressure. Well, the greater the back pressure, the longer the asphalt and the soap stay in the mill. I mean, and this is just a fraction of a second longer, but when you're able to keep your asphalt and your soap in the mill head longer, you can expect smaller particles, which is much better for your particle size distribution. You create more surface area within your emulsion, which means that you allow your emulsifiers to kind of do their job, and like with flow rates, the higher the flow rate, the shorter the residence time. So you may not see your tight distribution of particles, and I'll show you a graph here later on. But if you're having issues with particle size, you can always slow down your mill if you have the availability, and really allow that asphalt and that soap to stay in a little bit longer in order to get the proper shearing. Okay, it is important to understand your temperatures, for your asphalt and for your soap. So generally speaking, we have 3 different grades of asphalt that we use for emulsification: 64-22, 58-28, and a 52-28. And granted, I mean, this is just generally speaking. Obviously, there's cases out there where you use a much softer or a harder penetration, or your UTR is higher or lower based on your climate. But as a general rule of thumb, you want to make sure that whatever binder you use, the availability of pumping it is such that your viscosity of your asphalt is inducive to creating that emulsion. It's always helpful to kind of get a viscosity curve of your asphalt so you understand, as you begin to increase temperature, your viscosity will decrease. And as your viscosity decreases, your asphalt becomes easier to emulsify. But you don't want the asphalt to be too hot, again, because if it's too hot, then you will boil off your emulsion once it leaves the mill. Target emulsification temperatures usually are 185 to 203 Fahrenheit. Again, those temperatures can vary based on the amount of asphalt or residual you put into your emulsion, and also just the overall temperatures of your soap and your asphalt. And later on, I'm going to show you a slide here, and I think this is going to be available for everybody to look at after we're done, but the calculations on how to determine these critical temperatures. Within our industry, we typically use two different types of heat exchangers. We use plates, which is a picture you see here, or tube and shell. These are a great tool to have because what they do is they allow us to manufacture at elevated temperatures without boiling off our emulsion. And these are critical for when we manufacture mixing grade emulsions. When you have a mixing grade emulsion and you have too much heat in it, that means that you have too much energy. So when that mixing grade emulsion is now mixed with stone, then your reaction happens faster, meaning that your emulsion could break on the stone too quickly and clog up pug mills. So having a heat exchanger on hand or just part of the plant, in a lot of cases is critical. Now I will say, from experience that not every exchanger is the same, and not every exchanger plate is the same. So depending on what emulsion you're manufacturing, you may need to talk to the heat exchanger company and figure out if I'm making a emulsion that doesn't have much chemistry but has a lot of polymer in it, it may be shear sensitive. Meaning that if it's handled too much or if it's pumped too much, we begin to lose viscosity and create sieve. Well, some plates, the way there's like grooves in between each plate that kind of allow the cooling water to pass through and the emulsion to pass through. So you have rapid cooling, but there could also be a point of shear as well. And not every emulsion can withstand a lot of shear. So again, if you need to rapidly cool your emulsion, I would talk to your chemical vendor and or even your polymer vendor as well to kind of figure out what's the best type of heat exchanger for you to use. I will say that the plate exchangers, in my experience, are a little bit easier to use because if you do by chance clog up your exchanger, if you have a second set of plates laying around, you can probably swap out the plates fairly quickly. Whereas if you just have a tube and shell, and that tube and shell gets clogged up or gunked up and you have to clean it, that takes quite a bit of time to clean. So again, it's kind of personal preference on what works best for your situation. But again, heat exchangers are very, very critical for a lot of our applications and emulsions that we make. Mill gap. I'll talk a bit more in detail about the mill gap. And the picture on the right, you see the top is what we would call the rotor. Again, that's the part of the tooling that spins along with the tool bearing and or with the motor. The bottom is the stator. Now the stator, as you can see, has an opening, and that's where the asphalt and the soap are injected through the mill and sheared. Now the mill gap will vary based on the size of the mill and the manufacturer of the mill. Some mills are easy to adjust as far as either shortening your mill gap or, making the mill gap wider. The mill gap, basically the wider the mill gap, the more you can put through the mill, more throughput. But it necessarily isn't always the best thing for your emulsion. And if you're really trying to, get it in an emulsion with nice size particle distribution, there's other things that you can do to your manufacturing process that will really kind of allow that tight particle size instead of moving the gap. I'm not a huge fan of moving the gap because there are some mills if you do move the gap, you can kind of break the seal or it could start to leak. Not all are like that, but I think there's better ways, easier ways to reduce the size of your particles of your emulsion than adjusting the mill gap. But again, talk to your manufacturer, see what they recommend, because it may be as simple as putting on that more back pressure or adding 5 degrees to your asphalt or adding 10 degrees to your soap. Versus messing with the mechanic, versus messing with the mechanics of the mill and potentially rupturing a seal or a gasket. Back pressure. I can't stress enough how important back pressure is, especially from start to finish. Now, if you don't have a back pressure valve or a back pressure gauge, it's kind of difficult for you to, have back pressure from start to finish. Now, you will begin to build back pressure, as you begin to manufacture your emulsion, because, as you fill up your tank, you'll have the head pressure in that tank, so that naturally creates the back pressure. But what happens is so, for example, if you start up your mill and you don't apply back pressure, your particles of your emulsion won't be this nice tight distribution. Think of it like this: say you have 100, say you have two boxes, and in box one you have 100 pounds of a mixture of like baseballs and golf balls, marbles, basketballs, whatever, and then in the second box you have a mixture of like marbles and golf balls, both 100 pounds. Well, the first box with the large, basketballs, golf balls, softballs, that's going to have less surface area than the box than the second box with just golf balls and marbles. And the difference between the two boxes is that the box with all the different types of balls, that's the box of emulsion that didn't have didn't have back pressure consistent from start to finish. Whereas, if you have consistent back pressure from start to finish, you can expect your distribution of particles to be such that they're a lot more even. You have greater surface area in your emulsion, better viscosity. Hope it should have better consistency, and really allowing that emulsifier to work. Because if you have particles that are kind of all over the place, large particles, small particles, you're not really utilizing the chemistry that's intended. Plus, you're not really producing the best quality emulsion that you can. This is a graph that I wanted just to show you. This is off of a lab mill. We've got 3 different curves here. And as you can see, so the x-axis is the particle diameter. The y-axis is the volume, or the percent volume. But what this is showing you is that the faster your mill runs, the tighter your particle size distribution is. So basically, the more energy that you put into manufacturing, the more shear happens, and the smaller your particle size distribution. Now, I don't think you could possibly ever run a production mill at 12,000 RPMs. I think most production mills are around 3,600 RPMs or so. But just to kind of give you a comparison, the more shear that you apply, the tighter the particle size distribution, and again, the better quality generally speaking, that you have of your emulsion. In this slide here, I wanted to kind of show you the difference between two different types of mills. So you have two different flow rates with two different mills. Basically, like the lower the flow rate, the longer the emulsion stays in the mill, and the smaller the particle size distribution. So, if you have a mill that's sized for 12 tons per hour, but you're not really getting the consistency that you need, if you are able to slow down your mill to say 6 ton per hour and meet your shipping deadlines, that in theory should give you a better emulsion, better consistency. Again, you see the one here on the right with the blue, a 12 ton per hour versus 20 ton per hour. You begin to slow down your mill, you tend to get smaller particles. And again, when we say particles, our particle size distribution, what we do is we take our emulsion and we run it through a Coulter counter, and this measures. It takes like a snapshot of the emulsion, and it quickly analyzes the amount of asphalt that you have in there, and then it'll quickly determine like an average or a median of the asphalt particles in your emulsion. And really, for a good quality asphalt emulsion, you want your particles to be between like 5 to 7 microns in diameter. Sometimes a little bit more, sometimes a little bit less. But and also you want between 90 to 95% of those particles to be that size in diameter. The worst thing that you can have, and I'm going to go back, is to have a particle size distribution where you have in like the blue. That's kind of a bad day. That means that you have sieve in your emulsion, you have probably viscosity issues, you probably have quality and performance issues, and really what you want to see is that nice tight bell curve in the red. Here's the calculation that I mentioned earlier before, and this is a calculation, so you can determine your emulsion temperature, and it's also for soap temperature to achieve a particular emulsion temperature. So, with these variables, if you plug them in, it can be very helpful in determining what your temperature should be as you begin to manufacture. Now, again, this is in Celsius, so the one thing you're going to have to do is after you enter in your degree in Celsius, you're going to have to calculate to Fahrenheit if you use Fahrenheit. And I'm not going to go over the calculations, but they're there. They'll be available for anyone to look at. And then I think, Christine, you're up.
Okay, yeah, thanks, Joe. So let's just talk a little bit more about the emulsion, the chemistry and designing the emulsions. So basically, the way that you categorize the emulsion, depending on reactivity and particle charge, is really determined by the emulsifier that you choose and the recipe that you choose. So that's really how we classify emulsions and how we design emulsions. So if we look at the concept is that we want to match the reactivity of our emulsion with the reactivity of our aggregate. So for example, the first category is rapid setting emulsions. So cationic rapid set, CRS, or RS for anionic rapid set. So we're going to match these more reactive, faster setting emulsions with less reactive aggregates, for example, in chip seal. So if you think about a chip seal aggregate, those are larger stones, clean stones with not a lot of surface area, so they're not very reactive. But when we apply our emulsion on the road and then we put our chips down, we do want that emulsion to break really fast so that it can grab onto the stone and we can release that water. So as we move down the slide, we have emulsions that are less reactive, so medium setting, quick setting, slow setting. And we would match like a slow setting emulsion, a CSS for a cationic slow set or SS for anionic slow set with a more densely graded mix. because we don't want the emulsion to break before we can mix and apply the emulsion. So for example, with a slow setting emulsion, if you were making like a driveway sealer formulation, that has a lot of dense material, a lot of fillers, so we want a really slow and stable emulsion so that we can make that mixture and we can store it before we apply it, so we don't want it to break. Quick setting emulsions like CQS and QS are used for like microsurfacing, slurry surfacing applications. So this is also a dense graded mix, but we design the emulsion very carefully and match it really carefully with the aggregate that we have using a mix design so that we can really tailor that emulsion to get the reactivity and the breaking and setting characteristics that we want for that application, which has really fast setting. It's really a fast setting application. So a little bit more about naming of emulsions. I've got 3 examples here. So there are a variety of different emulsions that we use for different applications, and some of the naming is different depending on the state that you are in, and the different ways the emulsion is used. So in the first example, we have CRS2P. So this is a cationic rapid setting emulsion. The 2 is, this number is for viscosity. So 2 is for high viscosity, which is higher asphalt content, higher storage temperature of emulsion. And then the P means there's polymer. So that could be in the form of polymer that's dispersed in the asphalt binder. If we had CRS2L, that could be polymer in the form of a latex polymer. The next example is SS1H, so that's an anionic slow setting emulsion. The 1 is in this case for low viscosity, so this is lower asphalt content, lower storage temperature. And the H is the type of asphalt. So this is a hard, H means hard asphalt, like a PG 64 minus 22, got pen of like 40 to 90. In the last example, we have HFMS-2S. So this is an anionic grade because there's no C. The H is for high float. And what high float is you're using a special type of emulsifier that creates a gel structure in the asphalt binder. So that's what the high float means. MS is for medium setting. 2 means high viscosity, high storage temperature. And the S, in this case, can mean solvent, or in some regions it can mean polymer. So depending on the type of emulsion that we have and the application we're going to use it for, there's a number of different tests and specifications that we have. And really the purpose of these specs and tests are ways that we can determine if we've actually formulated the emulsion that we want, and we've got the properties that we need for our application, and we want to be able to try to predict how it's going to behave when we actually use it in the field. So one of the simplest tests is composition. So did we put the right amount of asphalt in it? So we test, asphalt, residue, solvent, by different methods like distillation or evaporation. And then handling and storage tests are tests like viscosity, storage stability, sieve. So they're answering questions like, can we pump this material and can we spray it? So viscosity is important. If you think about for like a chip seal application, we want the viscosity to be low enough so that we can spray it and we get a nice even coating, but we want it to be high enough that the emulsion doesn't run off the road when we apply it. So it's a really important measurement. Storage stability or settlement, so that's how the asphalt stays homogeneous when we store it. Like we don't want the particles to be settling out, so we don't want a lot of settlement. That's what that test measures. And the sieve is important. So in that test, we pour the emulsion through a screen and we see, are there any bits or shots on the screen? We don't want a lot of sieve because if we have a lot of particles, that means the emulsion isn't stable, and when we try to pump it, we could gum up our pumps, and we try to spray it, we can plug up our nozzles. So in terms of reactivity tests, these are tests that help us whether or not we've got the rapid, medium, or slow setting characteristics that we want. You know, we control reactivity in the emulsion by the choice of emulsifier and also by things like the dosage of emulsifier and the pH in the recipe. And we use tests like the demulsibility to characterize rapid setting emulsions. So this test, you take your emulsion and you add a solution of an opposite charge to your emulsion and you stir it and you see basically how much breaks. So that's giving you a measure of the reactivity of the emulsion. For the cement mixing test, so this test is used for a slow setting emulsion. So you're taking a portion of a very finely graded cement and you're adding your emulsion to it and you're seeing how much of it breaks. And in this case, you want very little of it to break in order to pass that test. Whereas demulsibility, you're looking for more of it to break to see that it's rapid. And there are different tests depending on where you are in the world. Residue properties, so with these tests, you're measuring, you know, did I select the right binder for the application? So we look at things like the penetration and the softening point of the asphalt emulsion residue to make sure we have the right viscosity. We also look for float characteristics and elastic recovery for polymer, those kind of things. So we just want to make sure that we have the right properties, the right flexibility and viscosity in the final asphalt binder that's left in our application. And then there are performance tests depending on the application. So, for example, for microsurfacing, there's a mix design with like a series of tests. And one of them is the wet track abrasion test. So you make a sample of your microsurfacing seal and you soak it in water and then you abrade it. So this is like the abrading action of traffic on the seal. So you're looking for moisture resistance here and the asphalt content. So depending on your application, there's a number of performance tests that are used to determine whether or not the design and the emulsion formulation that you've come up with are going to perform the way that you need them to. So the last thing I just wanted to touch on in terms of like chemistry for emulsions are, well, we design emulsions because we want them to be stable. We've talked about, transporting them and applying them and everything. But in the end, we really want them to break because we want to have the asphalt left in our application, in our road. We want the water to be gone. So there are different mechanisms by which asphalt emulsions break. Some formulas break chemically. So for example, cationic emulsions, more often that's a chemical break. So you have the cationic emulsion droplets have that positive charge on them. You mix them with aggregates, which tend to have a negative charge on the surface. The charge is neutralized by the opposite charges attracting, and the particles stick together and the emulsion breaks. There are other ways that cationic emulsions break chemically, for example, in microsurfacing too. There's pH changes when you use like cement filler. So those are ways that the emulsion breaks chemically. Some emulsions break mainly by the evaporation of water. So if we think of anionic emulsions, like an anionic tack, so that is the main mechanism of breaking is by the evaporation of water. In the picture at the bottom, as the water is evaporated from that system, the droplets get closer and closer together until finally they form a continuous film of asphalt binder. So really, probably in all cases, there's a combination of both of these mechanisms in the breaking and curing of emulsions. And we have to remember, too, that these mechanisms are affected by the environment. So at higher temperatures, chemical reactions are going to go faster. So your microsurfacing is going to, emulsions are going to be more reactive, your aggregate's going to be more reactive, things are going to break faster. You're going to have less time to mix and apply that microsurfacing unless you do some kind of adjustment in your formulation or use some kind of a break retarder. Then also wind speed and humidity have an impact on the evaporation of water. And then also there's mechanical factors like compaction. So when you apply a chip seal, when you roll the chip seal, that compaction, that mechanical effort is also important in helping to, initiate that break of the emulsion so that the asphalt binder can grab onto the chips in that process. So those are some of the mechanisms that are important to the breaking of emulsion. And back to you, Joe.
Okay, so the last slide that we have is storing and handling of emulsions. Now, AEMA, they have recommendations that they've published within their basic emulsion guide. If you don't have this book, I'd recommend that you go on to aema.org and buy this book. It has a lot of useful information, not just on storage and handling, but just on emulsion basics, chemistry, manufacturing, applications, so on and so forth. The one thing to keep in mind about, and I like to kind of talk about this, when you are storing and handling emulsion, you would want to treat it as if it was water. So you never want it to freeze, and you never want it to boil, okay? But for high viscosity emulsions, say like your CRS2P, HFRS2P, generally speaking, a good storage temperature is 125 to 185. Now, you can go higher than 185, but really, once you go past 185 Fahrenheit, you begin to evaporate off the soap solution or the water phase within the emulsion, and then your viscosity will increase. And then you might have skinning, and which can lead to sieves. So really, between 125 185 is what we recommend. You can go lower and higher. It depends. But then again, that's for the high viscosity emulsions. Lower viscosity emulsions, you can go as low as say 50 Fahrenheit or ambient temperature during the fall. And sometimes as high as 140, even higher than that. But again, it depends on the emulsion. It depends on the chemistry and the application. When we store emulsion long term, vertical tanks are by far the best option versus horizontal tanks. Vertical tanks, you'll always get at the top of each tank, like this skin or this heel that kind of floats up and down as the emulsion volume increases and decreases, but that skin doesn't really grow a whole lot. Versus in a distributor, that's either in a transport distributor or a distributor for chip seals or whatever. Those are horizontal tanks, and as the volume of emulsion increases and decreases, so does the surface area at the top, which can really negatively impact and affect emulsion quality if that skin is kind of left unchecked. That can and will develop when emulsion is exposed to the air. So again, for long-term storage, vertical is definitely the best. Agitation in our tanks, in our soap tanks, in our emulsion tanks, there's a lot of debate. Some folks just absolutely hate having mixers in tanks. I am of the opinion where I love to have a mixer in a tank. The thing though is that if you do have a mixer in a tank, make sure that mixer is very slow RPMs. You want big blades. You just want really slow movement. You don't want actual mixing. Never create a vortex in a tank of emulsion. And it could be a top mount mixer as well, but I would also recommend having a timer on that mixer, just so it cuts off after 10 or 15 minutes. So say, for example, if you have a tank of CRS2P and you kick that mixer on and that mixer runs all night, you can expect that viscosity to be much lower in the morning. And now you potentially ruin an entire tank of emulsion, whereas if there was a timer on that mixer, that would have saved that product. So definitely recommend having a timer on your mixers. Any foams can help. Usually they are incorporated into the soap solution prior to emulsification if you have foaming issues, but they can also be post-added as well, especially when you're filling up your distributor or your tanker truck at the loading rack. But if you are experiencing foaming at the loading rack, one thing to kind of keep in mind is, like, say if you're at a bar, right, and you're getting a beer, you want to have that glass at an angle as the beer is being dispensed, because that kind of mitigates the foam. Same thing with emulsions. Just the beer tastes better than emulsions. But anyway, moving on. Never mix cationic or anionics. As Christine mentioned, there's a electrical charge between or associated on the asphalt of cationic being positive and negative for the anionic, and opposites do attract. So if you have, say, a tanker truck that's has a significant heel of anionic emulsion in that tanker truck, and then you load cationic on top of it, chances are the asphalt's going to want to come together. You aren't going to have this big explosion or anything, but what you're going to have is that now you can't pump that broken asphalt off that tanker truck, and you have a real mess on your hands. So you definitely make sure that say if you do have a trailer that you use between cationic and anionic, make sure that heel on that trailer is as low as possible and or dry. Never add hot asphalt to emulsion. That's dangerous. You can get somebody killed. It will boil off, and potentially kind of rupture like a volcano. So always make sure that whenever you load a trailer, you know exactly what's in the trailer before you load on top of it. And then can I dilute my emulsion after it's been made? Now, the answer is it really depends. It depends on the type of emulsion that you manufacture. It depends on the chemistry. I will say though that if you add water to a emulsion that's rapid setting, which generally speaking there isn't as much chemistry in versus a slow setting chemistry or a slow setting emulsion, the emulsion can begin to separate out, kind of phase separate. So you're limited on the time that emulsion is able to be used, or pumped if you do happen to dilute. Now, again, it also depends on what the application is, if the state DOT allows it. There's a lot of depends, but and some emulsions are manufactured just so they can be diluted, and some aren't. So I know that isn't really a absolute answer, but there's a lot of depends within that question. So anyway, I think this kind of wraps up our presentation, and we have a few minutes left for questions. So I thank you for your time, and Christine, I know she thanks you as well. I'm sure she'll jump on, but it was great to do this, and we definitely appreciate the opportunity.
Joe, we have one question from Nick. It says, is there a typical asphalt mix design used when creating an emulsion, aggregate size, etc.?
So say, for example, microsurfacing, slurry seal, recycling. Yes, there's mix designs that need to be done, prior to really the manufacturing of your emulsion and your application of the material. Again, it kind of depends on what you're manufacturing, but I mean I can't really think of any states that don't recommend or require rather mix designs for these applications. Again, for microsurfacing slurry, especially for cold in place FDR. some states require a mix design for chip seals, not all. So hopefully that helps.
Yeah, and to add that, like ISSA has guidelines for mixed designs for micro and slurry that you can see on their website.
If there are any additional questions, please use the chat function.
Ali, I've put all the questions over the presenters pod that happened during the course of the webinar.
Would you mind reading them? I don't see them, Tony.
Okie doke.
Thank you.
What will be an example of stabilizer for foam creation?
I think I can answer this one in terms of so stabilizers that you would add in the soap would be perhaps like a thickener or a co-emulsifier. So those are typically added in the soap solution, and they help. Like a thickener will help stabilize the emulsion by thickening the water phase. An example of one would be like a cellulose type of thickener, which is comes from like a plant. It's a plant-based material, and it's like a water-soluble polymer. So they would help thicken and stabilize the emulsion. And I think the function of like co-emulsifiers are, in terms of stabilizing the emulsion, like they can be used for if you need a really like slow setting emulsion, like for like a driveway sealer, you might need to use a primary emulsifier and a co-emulsifier to be able to have that emulsion be stable enough to add like the clays and the silica and the fibers and all the things that are added to a driveway sealer type of formulation.
Thank you, Christine. Next question, what are the white pipes at the bottom of the soap manufacturing tank?
The white pipes, those are the heating coils. The one thing I didn't mention about the heating coils is, they can either be steam through the coils, hot water, or hot oil. So those are coils to heat the emulsion. I'm sorry, to heat the soap.
So the next question is related. The heating at the soap tank is required at all times for soap, or it is required only due to cold weather?
Well, I mean, I don't necessarily think cold weather really dictates the temperature of the soap. What really dictates the temperature of the soap is what emulsifier you're using, and also, what type of asphalt you're using as well. So, again, it kind of depends. I've seen enough, and and I'm of the opinion that having a warm soap solution, you're just much better off as far as the emulsion quality. But I mean, I have seen it where you can make an emulsion that's of good quality with a fairly cold soap solution. So it kind of depends. I mean, I think you're kind of putting yourself at risk if you do have a cold soap solution. Warmer, I think, is just generally better.
Perfect. Next question. For a CSS 1 HP emulsion, what will be the ideal or required targeted pH?
Kristen, you can jump on this, but the one thing I've seen is typically it's 2 to 2.5, but it depends on the emulsifier and the stone. And Christine, you want to add to that?
Yeah, I mean, typically you start off at 2, but you might have to adjust it in order to adjust, to match the reactivity of the stone.
Okay. Next question, is it okay to add water in the tanker after it is milled to lower the viscosity? I covered that a little bit earlier. I think it depends on what you're manufacturing. Some emulsions can handle being diluted, and some really can't. So I would say try it out in the lab first,
it kind of depends on the end application, what you're trying to achieve. There really isn't any mixing that'll happen if you add water to a tanker truck, and then if you begin to kind of slosh it around, that will help out with mixing, but then it'll also create foam. So order of addition is important. When you do dilute your emulsions if you need to. So I would recommend speaking with your chemical vendor, and then also trying it out in the lab first to see what happens.
And the last question I have here, is there a typical asphalt mix design used when creating an emulsion, such as, aggregate size, etc.?
Yeah. I mean, I guess it depends. And, we have, most states require designs for microsurfacing slurry, like CIR, FDR. So most mixing grade systems require mixed design. Some chip seals do as well, not all.
And one question that just popped up right now, for seal coating, does the base oil play a part in how sticky the residue will be? Basically, what role does the residue play in holding stone beside buried in residue?
So can you just repeat that? I didn't hear the last part of that.
For seal coating, does the base oil play a part in how sticky the residue will be? Basically, what role does the residue play in holding stone besides buried in residue?
Well, I think the type of asphalt binder and I guess we were talking about chip seal, right? So it's like you tend to use a softer asphalt binder in a chip seal formulation, and part of it is to have a good good adhesion onto that chip. So I think that's what the person is asking. So I hope that answers the question.
Okay.
Well, and there are some asphalts that are more naphthenic, more paraffinic in nature. So typically the asphalts are kind of waxy. They don't like to grab onto stone as well as like your naphthenic asphalts do. So and again, depending on the asphalt, the crude source, where it came from, there are additives that you can add in order to increase adhesion to your aggregate.
Yeah, and to add on that too, like the emulsifier that you have in the chip seal emulsion, that tends to be like a natural adhesion promoter to help promote, good, adhesion to the chip. And then also when you have latex in the formulation, that also is another component that helps, have good adhesion of the chip in a chip seal.
Got one more question. Is adhesion, is it related to the surface charge?
Yes. So in some cases, when you have a negative charge on it depends on the chemistry of the aggregate as well as, and matching it to the chemistry of your emulsion. So aggregates, depending on, their chemistry, like an aggregate that has more silica, that's more acidic, it's going to tend to have more of a negative surface charge than something that's more limestone-based. So they will have better affinities for emulsions that have the opposite charge. So like a cationic emulsion will have better adhesion to more of a silicious type of a stone. And then for limestone, like types of aggregates that have more limestone, a different chemistry would have a better adhesion to that type of stone. So yeah, there's different chemistries to the aggregate, there's different charges on the surface, and there's other things that influence also the charge on the surface. such as whether the aggregate is freshly crushed. Because when it's freshly crushed, it tends to have more of that charge on it than as it ages in the stockpile.
Fantastic.
And also the one thing too, if you can, for chip seal, for seal coating emulsions, is that if the stone's very dirty, if there's like high fines, high dust, and that stone isn't washed, that can adversely affect the adhesion between the binder and the stone. So typically for like chip seals, we like washed stone, crushed, single sized. So dust can also be a deterrent as well for adhesion.
Fantastic. For all those who are asking for the presentation, it's up on the pod right above the chat. It's the second document. You can download and print it whenever you want. There's a last
We've
question.
got one more question. Oops, go ahead.
Go ahead.
We did record the webinar, and we will be providing it to all attendees once it becomes available.
What is the dust percentage that you target?
That's a good question. Typically, gosh, what is it? There's a good study done down out of the University of Colorado on by Dr. Schuler on the ideal amount of fines on your gradation, and I'm sorry, I don't have that percentage off the top of my head, but I mean generally cleaner the better. It doesn't really answer that specific question in great detail, but generally speaking, cleaner the better.
Perfect. Just one question that I'm going to have of the audience. If I noticed that there were a couple of people that actually were sharing or presenting the webinar through a one site with multiple people. We'd love to know who these people are and how many we had, so that we can get an accurate count for the webinar. So I am going to post here my email address, and if you were one of those, send me an email. And there's one more question over here. We got time. How moist is it too moist? That's another good one, Joe.
Well, if it's, if there's water, running off the stockpile, then that's just way too wet. So, designs will help, give you a range of, how wet your stockpile can be. Because, one of the tests that we do for microsurfacing and, slurry is a bulking effect or a quantitative effect on moisture. So, on the stockpile itself, and that's a good test to have done as far as your aggregate analysis. And, some aggregates are more absorptive than others. And so, again, it depends. But I would definitely do your lab work first, before you go out there. And generally speaking, dry stockpiles really aren't a good thing, and soaking wet stockpiles aren't a good thing either. You just want a nice balance, nice damp stone.
I think that is it in terms of questions. I have posted a slide here. This is our next webinar, Milling Best Practices, on March 19th, same time. Visit either one of these locations right here to register, and keep in touch with other additional webinars that will come in the following months.
We'd just like to say thank you so much to Joe, Christine, and FHWA for helping us host this webinar today. Again, all the presentation was recorded and will be sent out via email once available.
Thank you, everyone.
Thank you.
Thanks.
Thank you.
Thank you. All right. Bye-bye.
Okay, bye.